Bam! Mr. Tarrou. In this lesson, we are going to be looking at graphing absolute value functions using transformations. Now, I've already done a lesson about graphing absolute value functions, but in that particular lesson, we were graphing them using a table of values, where we first found the sharp bend, which every absolute value function has. I'm looking for a sketch up here already. And then building a t-table off of that and just simply plotting points. I'll put a link to that lesson in the description of this video. Well, here we're going to try and sort of not draw graphs or make graphs of absolute value functions, but a sketch of them using these transformations. In this lesson, we are going to be doing, let's see here, we got 1, 2, 3, 4 examples of graphing an absolute value function just with the knowledge that we have of transformations. We're going to do a fifth example, which is not going to really be a parabola or absolute value function. It's just going to be sort of a generic function which we're going to manipulate with a couple of transformations, because the effects that we get from A, which can be a vertical stretch or compression on our graph, and the value of B, which is going to be a horizontal compression or stretch, it can be a little bit confusing, especially with these, all these examples are going to be linear absolute value functions, and it's going to seem like the horizontal stretch and compression is doing the same thing as a vertical stretch or compression, and that's really not the case. So I want to clarify that with you over the fifth example. Then we're going to be looking at the equation of the parent function y equals absolute value of x. I'm going to tell you or give you some transformations that's been applied to that function and try and come up with not the graph, but the equation with those transformations applied to it. So the overall overview of these transformations, which by the way, the effects of A, B, C, and D are going to be the same regardless of whether it's an absolute value function, a log function, a parabola, a trig function like sine y equals sine of x. So if you understand your transformations really well, you can sketch hopefully pretty much any graph, any function that you would see in an Algebra 2 or pre-calculus, or even calculus class for that matter, as long as you know what the parent function looks like. Okay, so what do we got here? We have y is equal to, and some textbooks will have a little bit of a different notation. Sometimes the textbooks will have this value of b inside the parentheses, and so it'll be like maybe plus or minus parentheses bx minus c. And if this idea of b is inside the parentheses and the coefficient of x is not equal to 1, well then these rules are going to vary just a little bit. So it'll still apply, but you know, textbooks will vary. I'm being consistent with the ones that I'm teaching from at my school. If your leading coefficient is positive or negative, well, if it's positive, then you're not going to have any transformation at all. But if your leading coefficient is negative, what it's going to do is take your parent function and it's going to reflect it over the x-axis. We'll look at the what a parent function for absolute value, linear absolute value functions are in a second. It's going to be y equals absolute value of x. If that leading coefficient is negative, again, it's going to reflect our graph over the x-axis. So instead of, well, this is bothering me that I don't have a parent function already up here. The parent function for a linear absolute value function is y is equal to the absolute value of x. Now, the absolute value function tells you how far a number is away from 0 on a number line. That's really what an absolute value function does. But ultimately, it kind of just always seems like it's getting rid of the negative after we simplify everything that's inside of that absolute value function. So if an answer or a value is put in here which is negative, after you simplify everything inside the absolute value function, it makes it positive, because a distance from 0, any distance for that matter, cannot be negative. You'll sometimes see negatives in front of a number, and that may indicate the direction of movement, but not the actual distance. If you think about graphing y is equal to mx plus b, and there's not a lot going on inside this absolute value function, so we can lose the idea of a generic m or slope and just let the slope equal 1. And if we look at, again, we're talking specifically linear functions, so y equals mx plus b, graph in a line. We got a y-intercept which is 0 because there's been no vertical shift, and our slope is going to default to a value of 1. So if you want to graph y is equal to x, well, that line is going to have a y-intercept of 0 and a slope of 1. So we're going to put a dot here at 0, 0 for our y-intercept of 0. The coefficient of x, or m, is equal to 1. So I have, if you're not sure about graphing lines, I'll put a link to graphing linear functions or y equals mx plus b down in the description of our video as well. So we're going to, from the y-intercept of 0, go up 1 and over 1, and up 1 and over 1, and so on and so on. And if I connect all those dots, we're going to have a straight line that looks something like that. But you see, I'm starting to, where my x's are negative, of course, since there's not much to this equation, y equals absolute value of x. Why am I drawing y equals x? Because it's really the same, except, graphing y equals x and graphing y equals the absolute value of x, it has a lot in common, except when the x's get negative and where normally we would have negative y values, before we come up with our final answer or value of y, we're going to apply the absolute value function, which is going to basically get rid of all those negatives. So instead of dropping below the x-axis, we're going to reflect off of it, and this is a sketch anyway of the parent function. This is y is equal to the absolute value of x, and I just wanted to point out that really all we're doing is graphing a line, but when it hits the x-axis and those y values, which would normally become negative, the absolute value is going to make sure that those remain positive. Now that's not to say that when you graph absolute value functions you'll never have a negative y. This is the parent function. There's been no vertical transformations or shifts. Okay, so now that we have a parent function to look at, let's try this again. If our leading coefficient is negative, that's going to reflect the graph over the x-axis. So instead of opening up, if you will, it's going to open down. If our leading coefficient in front of, what's in front of the absolute value function, if that is greater than 1, we're going to have a vertical stretch. It's going to sort of, our last little ditch effort after we simplify everything that's going inside, happening inside this absolute value function, it's going to take all those, what's eventually going to be our y values, and pull them up. It's going to make those, it's going to move those points twice as far away from, or 3 times as far, or half as far, whatever a is, from the x-axis. So that's going to be a vertical stretch, and if a is between 0 and 1, that's going to be a vertical compression. Now notice I'm talking about a being greater than or equal to 1. The negative part of the transformation of our leading coefficient is going to be the reflection. We have a plus or minus b, which my textbooks will have that in front of the parentheses and have the coefficient of x be 1 again. If b, or except if that little coefficient, now we're inside the math function. The main math function going on here that we're talking about, of course, is those absolute values. If that negative is out in front of that math function, that's a reflection over the x-axis. And if you have a negative, though, that's inside the math function, this would be true for logarithmic functions, square root functions, parabolas. That's going to be a negative coefficient in there is going to be a reflection over the y-axis. We'll have one of those in this video. And if b is, again, in front of that parentheses, and even if it was inside the parentheses in front of the x, if that b is greater than 1, that's going to be a horizontal compression. Transformations inside the math function kind of always do the opposite of what you expect. If this leading coefficient out in front of the absolute value function is more than 1, it's going to be a vertical stretch. If you have a coefficient inside the absolute value function, or this could be square roots, it could be the logarithmic function, then that is going to be, well, wait a minute, bigger than 1 was a vertical stretch, but bigger than 1 inside the math function is a horizontal compression. So kind of like the opposite of what maybe you might think. And if your b value is between 0 and 1, that is going to be a horizontal stretch. You play around a lot with this coefficient of b when you are graphing your trig functions, sine, cosine, tangent, secant, cosecant, and cotangent. It helps you determine the period of those periodic functions. Now, again, if your b is in front of these parentheses and the coefficient of x, which is inside your main math function, is set equal to 1, then you can just simply look at the plus or minus that's with that c and understand that that is a shift to the left or the right. So if you have x minus c, notice that's in the sort of standard form. You might look at that and say like x minus 2, oh, you're subtracting 2 from the x's, so it's going to move the graph, to the left as if you're going into the negative direction, but the negative's already in that parent function, and that would be a shift to the right. So x minus c is going to be a shift to the right c units, because the minus, the negative, is already in this sort of standard form for transformations, if you will. So if you have x minus c, really that means that the c value is positive. And if you have x plus c, then the c value that is in here would have to be negative to cancel with the negative that's already in the formula. So that would be a shift to the left c units, because actually c is negative and not positive. See that backwards and forward, that's sort of reverse of what you might expect, or the opposite of what you might expect for these transformations that are inside your math function. In this case, absolute value, could be square root, could be logarithms, etc., etc. If you have a plus or minus of some kind of constant, and it's not inside the math function, it's not inside the absolute value function, then that is going to be a shift up or down. And if you have a plus something, it's going to shift it up. A minus, it's going to shift it down. Now, looking at our parent function, y is equal to the absolute value of x, our very first example is a very straightforward one. We've got y. Our leading coefficient is still positive, so we're not going to do any kind of reflection. It's 1, so there's no vertical stretch, if you will. There's no plus or minus inside the absolute value function, so there's no left or right movement. My coefficient of x is equal to 1, so there's no horizontal compression or stretch. The only transformation that we're looking at in this equation is the minus 3 that's at the end of the equation. It actually can be at the beginning, too. It could be written as, I'm going to have to erase this to have room, but it could be written as y is equal to negative 3 plus the absolute value of x. It doesn't matter that it's at the end. What matters is we have a subtraction of 3 that's not inside the math function. And that means it's a vertical movement up or down. And so you're going to plug in an x, you're going to take the absolute value of it, and then you're going to take all of those answers, before you finalize all your answers of y, you're going to take whatever that is and subtract 3. So all of your answers, all your y values are going to get smaller by a value of 3. So, hopefully we have enough clear distinction between the white and the yellow on the chalkboard here. But that point at 0, 0, because of that minus 3, is going to get moved down 3 spaces. This point at 1, 1 is going to get moved down 3 spaces, so it'll be at 1, negative 2. And then we'll be at, instead of 2, 2, over 2 and up 2, we'll be at, counting down 3, we'll be at 2, negative 1. And these points will also move down. And this is a sketch of, and thankfully I've got some graph paper up here on the board from my little pull down here. That is, the white one, a sketch. I didn't have to make a t-table. I just knew what the parent function looked like and moved all the points down by 3 units. Now, just because so many students struggle with it, I wanted to do a little domain and range review that you can pull that information out of the graph. This graph moves left and right forever, made up of an infinite number of points. And so as it opens up, it's going to include all the individual x values that are in these points that are included in the graph. Not just the where the x is, where the vertex is, not just the x-intercept, but the actual continuous graph itself. The domain, D, is going to be from negative infinity to positive infinity. The domain, the x's which are included in this white graph, is going to be all real numbers. That's what it looks like if your book is using interval notation. Now, as far as the range goes, domain is the horizontal movement, the independent variable, the x values. The range is going to be well, I guess you could say the opposite, the up and down movement, the dependent values, the y values. So, we don't always call the x and y axis. It could be, like a word problem application. The range values, the y values that are included in this graph, well, it goes up forever. So the y values are just going to get bigger and bigger and bigger. But the smallest y value that's included in this graph is, looks like negative 3. So one way of writing this is y is greater than or equal to negative 3, but with interval notation, that is going to be a square bracket that indicates equals to. The smallest y value is negative 3, and then the graph goes up forever. So now we have not only a sketch using transformations, but we have a little review of domain and range. Now we got 3 more examples. We'll do 2 at a time, I think. I don't know, whatever. But we have 3 more examples. I'll go a little faster of sketching absolute value functions with transformations. Bye! So for our next two examples, we are going to first graph y is equal to the absolute value of x, or sketch, the absolute value of x plus 3 minus 1. And we got our parent function up here just so we can see the movement with our transformation. We have a plus or minus that is inside the math functions, and I'm talking about those absolute value functions, and we have a plus or minus that's outside the absolute value function. And this -1 could be out front as well, like -1 plus absolute value of x minus 3. So this, remember, the parent function was, or that sort of standard form with all the transformations, was x minus c. Well, that's going to be the absolute value of x minus -3 minus 1. Now, maybe do this once or twice for teaching purposes or learning, but I would not do that in a normal problem that I'm working on. But I'm just trying to point out that that plus 3 is not going to move the graph to the right 3 units. It's going to move it to the left. So we have a transformation of left 3. And this plus or minus that's not in the math function, square root, absolute value, log function, parabolas, whatever, powers of 2, that is going to be a shift up or down. Well, that's minus, and that moves in the direction you kind of would think. Plus is up, minus is down, so we're going to go left 3 and down 1. Okay, so every point on this parent function, left 3, down 1. So let's start with the most obvious, where the sharp bend is at 0, 0. Let's move that left 3 and down 1. We have a point at 1, 1. Let's go left 3, 1, 2, 3, and down 1. Over here, we're at -1, 1. And so 1, 2, 3 to the left and down 1. And just as a quick sketch, we are looking at a graph that looks something like that. Oh, I got to miss the grid there a little bit. Now for that green graph, the domain, this is opening up forever. This graph will include all of the possible x values as it moves left and right, because the horizontal axis is basically our x value. So domain is going to be from -infinity to +infinity, and the range, that graph goes down. Well, this first original parent function goes down to 0, 0, so the smallest y value is 0, but now the smallest y value is -1, and it goes up from there. So the range is either y is greater than or equal to -1, but a lot of my textbooks are using interval notation, so -1 to infinity. When you do interval notation, the lowest value is always first, and then the highest value is last. Now with this second example, this blue function here, we have y is equal to, I hope this is green and blue, I hope that's showing up in the camera. We have y is equal to -2 times the absolute value of x minus 1 plus 4. Okay, now I'm going to verbalize all these transformations, give a sketch, and then I'll step off and write them all out in case you need to see that. We have a sort of thinking about order of operations as well. What would you do first? You put a number in, you do subtraction inside the parentheses, then you do your multiplication, and then your vertical shift. So inside here, that's x minus 1. That's going to shift the graph to the right. So this point at 0, 0 is going to go to the right one. It is going to, all those values are going to get multiplied by 2, or have a vertical stretch of 2. We also have a reflection over the x-axis. So let's see here. How do we want to do this? I guess we could do this in stages. Let's try and do some different colors. Let's first talk about that horizontal change of 1. That's going to move this vertex from 0, 0 over to 1, 0. And if that's the only transformation we would have, then the graph would look something like that, with the slope of the lines coming off of that vertex having a slope of 1. Then we're going to reflect it over, this is going to be a big old mess by the time I'm done. We're going to reflect that over the x-axis with that leading coefficient, which is negative. And we're going to put a vertical stretch on it of 2. So instead of from this vertex, there's also, I understand, a vertical shift up and down. We'll take care of that in a minute. So at 1, 0, instead of going up 1 and over 1, instead of the graph opening above the x-axis, it's going to open down because it's been reflected, right? And instead of going over 1 and down 1, because of that vertical stretch of 2, that a value is bigger than 1, it's going to make all the points twice as far from the x-axis. It's going to, literally just vertically stretch it out. So instead of up 1 over 1, instead of over 1, down 1 and over 1, we're going to go down twice as far, 2, and go over 1. So again, instead of up 1 and over 1, we're going to go down not 1, but 2 and over 1, and have that balanced and go in each direction. And so far, our graph would look something like this if we just were doing the application of the horizontal shift and the reflection over the x-axis and the vertical stretch. But now we got to take in this account that we have a +4. That's going to move the graph. Of course, this plus or minus is not inside the function, so that's going to move the graph up. So every one of these points is going to go up 4. So instead of being at 1, 0, we're at 1, 2, 3, 4. We're at 1, 4. Instead of being at 2, -2, we're going to move that up 4 and be at 2, 2. And this should be in another color. I think I was going to have my final answer be in blue. And this is going to get moved up 4. And I got a lot going on trying to show you the individual steps. But this is going to be the final sketch of this absolute value, linear absolute value function. And I keep saying linear because inside the absolute value function, this is just x to the first minus 1. There's no other variables going on, and the coefficient, or excuse me, not the coefficient, but the exponent is equal to 1. So it's a linear function inside the absolute value function. So let's clean this up just a little bit, and that's about as good as we're going to get it. That blue line is the sketch of this absolute value function. And if you don't like doing these problems with transformations, you can always make a t-table. Find that where that sharp bend is by setting the inside expression equal to 0, and build a t-table off of that with that x value of 1 being your center. The domain of that graph, it's opening left and right forever. So your domain is going to be equal to, one more time, -infinity to +infinity. And the range, now that graph is opening down. So when you talk about your range, remember we said the first number in your interval notation needs to be the smallest. Well, coming up from the bottom, this graph extending down forever, your smallest y value is going to be -infinity, and it's going to keep rising until it gets up to a y value of 4, bounce off that, and go down again. So the biggest y value included in this blue graph is 4. And there's a solid dot there, so it's going to include 4. So our range is -infinity to 4. Voila! One more example like this. So here we have examples 4 and 5. We're going to sketch the graph of y is equal to the absolute value of 2x minus 6. Actually, you can leave it in this format if you like, and still get a correct sketch of what this absolute value function will look like. But let's put this in the format that I prefer and keep all of the examples consistent. And that means that I need to have a leading coefficient of my x inside here equal to 1. But right now it has a coefficient of 2. So we're going to factor that out of these two terms. We're not going to pull it all the way out of the absolute value symbol, but just leave it sit there inside. So we're going to have y is equal to the absolute value. We're going to take 2, the common factor which is shared by these two terms, and divide it out. So 2x divided by 2 is equal to 1x. And well, let's see here, -6, I don't know why I'm pausing, divided by 2 is equal to -3. And now when you look at this, and we have a sketch of our parent function up here on our graph, then we can see that we have a b value which is equal to 2. That is going to be a horizontal compression. And what that is going to do is it's going to take, now it's a horizontal compression, so it's going to take all of the points and move them sort of twice as close to the it's going to make the distance from each of the points from the y-axis half the distance. So instead of having a point here at, well, I can take, half of 1 and get it to be 0.5, but here we have a point of 2, 2. Well, if you go over 2 and up 2, if you go over 2, the distance from the y-axis is 2. But we want to reduce that by a division of 2, if you will, because this isn't a stretch, it's a compression. So we're going to divide by 2 or move that distance, reduce that distance by half, effectively dividing the distance by 2. And instead of having a distance of 2, we're going to have a horizontal distance of 1. And so if we look at just the effects of this, this b value of 2 compressing the graph horizontally, you would see a graph that looks like this. And I'm going to dot it because we're not really done with the sketch. Now, so we've applied that horizontal compression of 2, and now we're going to take and realize that we have a x minus 3. We have an x minus c. That minus 3, well, actually it's a c value of positive 3. That x minus 3 needs to indicate that the graph to you, that the graph is going to translate 3 units to the right. And so this point at 0, 0 is going to come over here and be at 3, 0. This point here, instead of being originally at 2, 2, is at 1, 2, is going to get moved 3 units over to the right. So 1, 2, 3. And this point is going to get moved 3 units to the right. 3 units to the right. So 1, 2, and 3. Hope you can see my graph paper grid on the camera. And my sketch is going to look something like that. If I've done a, I'm not using rulers, but and I can see I can miss there. So it's just a sketch, okay? Our vertex is, though, at 3, 0. The domain of this graph is going to be all real numbers. And the range, the smallest y value that's included in all of the points that make up this graph is 0. And then we're going to go up from there to infinity and beyond. Now, over here, I'm a little bit bothered by, whoops, oh, chalk down. I'm a little bit bothered by the fact that, especially because these are linear functions, that the effects of the horizontal compression really looks like a vertical stretch. And you will see how that's not actually the case, say, when you graph sine and cosine, those trigonometric functions, among other examples. So what I want to do here is I want to clarify the difference between a vertical stretch and a horizontal stretch in compression. A lot of students, when they see a parabola, like they graph y, I know we're not doing parabolas, but when they graph y equals x squared, could have done this on the previous screen, and then they graph y equals 2x squared, it makes the parabola look like it's skinnier. Just like, well, we kind of see that here, but that's a compression. So on the previous screen where we had a vertical stretch on our absolute value function, it took the v and squeezed it in. Actually, kind of exactly the same as it looks here. And it appears like the absolute value v shape, it's only a v shape because the inside function is linear, appears to be skinnier. Now, it kind of is skinnier with a horizontal compression, but if it was a stretch, it would not be. So you'll see that difference again with sine and cosine waves, maybe some logarithmic functions, maybe. But to really stress that, in our last graphical example, I've given us sort of just a not an absolute value function or a parabola or a logarithmic function or a sine function. Just here, this is sort of a basically looks like kind of like a polygon, except there's no line segment along the bottom. And we have a 3-sided graph, and I'm going to call that function f of x. And given the sketch of the sort of generic, it's actually not a function, that would fail the vertical line test, it's just a graph, a relation. We want to sketch g of x is equal to 2 times f of x. Well, now, this multiple of 2 is not inside the function, it's not inside the absolute value function or whatever function you're dealing with in your particular equation. Of course, you probably chose this video because it said absolute value. But this 2 is outside the function, so it's in front of a square root. It's in front of a logarithmic function. It's in front of an absolute value function, and that means that this is an a value of 2, and it's going to vertically stretch the graph. Not make it skinnier. Vertically stretch the distance that each point is away from the x-axis by a multiple of 2. Well, this point is at or has a y value of 0, so 2 times 0 is 0. This point has a y value of 3, so you take that and double it, and you're going to have a y value of 6. I didn't put my tick marks here on my graph all the way up. Again, this y value of 3 is going to become 6. And this, hopefully you can see that it's purple. Graph, sketch, whatever you want to call it, is a representation of g of x. G of x, which has got a vertical stretch applied to it, or applied to function f to get function g. Here, now we have a multiple of 2, but it's inside the function, like we have here with our absolute value. We have a multiple of 2, a leading coefficient of b. It's not a leading coefficient, that's in front of the entire equation, but we have a multiple on our variable x, which is inside the math function of 2. Now that's a horizontal compression. And if it were a 1/2, then all the points would become twice as far away from the y-axis, because if b is between 0 and 1, it's a horizontal stretch. Okay, so let's see here. I got this in green, and if we have a b value of 2, and that 2, which is greater than 1, horizontal compression, all the points are going to get moved in. The horizontal distance that each point is away from the y-axis is going to get reduced by a division of 2. So this has got, again, a horizontal distance of 2. Now it's a horizontal, whoops, that's not function f. This has a horizontal distance of 2. Now it's got a horizontal distance of 1. This might look a little bit sloppy by the time I'm done. I hope not. Here, to get from the origin to this point, again, that was a distance of 6. Well, now that's going to get divided by 2 because b is 2. And it's going to become a distance or x value of 3. And this, hopefully you can see, green graph is a representation of h of x. And now finally we have quite a bit more going on here. We have, let's sketch or graph what k of x looks like, given the fact, okay, we have our parent function f, the white, which is sort of hidden in there between the green and the purple graph now. And we want to take function f. We have a -1 value of b, so that -1 coefficient of the variable x, if you will, or inside the math function, whatever it may be. In this case, it could be like you're inside your absolute value function again. That's going to reflect the graph over the y-axis. And in here, you have a +3. That's going to shift the graph to the left. And so, knowing that this is our parent function of f of x, this white sort of straight-sided thing, let's reflect that over the y-axis and shift everything, because I've already got so much stuff on there, I'm going to do it all at once. Reflect it over the y-axis and shift everything over to the left 3, because here this would be like f of negative x minus -3. Your c value is -3. That's to the left. So instead of being at an x value of 2, the reflection over the y-axis is going to make that an x value of -2, and then 1, 2, 3. Let's move it over 3 spaces. We have an x value of 0. That's going to reflect it over the y-axis, so that's still going to be an x value of 0. Move it to the left 3, and we are right here. This point, which is +6, is going to reflect, and we're going to be at -1, 2, 3, 4, 5, -6. Oh, I've not made my graph paper big enough. And then we're going to move that to the left 3 units. So 1, 2, and out here 3. Just squeeze that in. And likewise, we had a vertical line segment here, so the other point is going to be right here. And this orange graph is our representation of what k of x would look like if we took function f, applied a reflection over the y-axis, and shifted the graph to the left 3 spaces. Now, some textbooks, maybe, I'm thinking of how my the pre-calculus book I teach from sets up the standard form for trig functions. You may see this like f of -x minus 3. And in that form, we have a shift to the, you would kind of do the slide first, and you would take this point, say here, and with the x minus 3, move it over to the right 3 units, and then apply the reflection over the y-axis, and end up at the same point. I much prefer this notation. I don't know why, I'm just showing you this in case maybe your textbook uses that. Now, our last example, we're almost done, thank you for watching, is going to be I'm going to give you some transformations that need to apply to a function, and we're just going to write the equation represented or created from those transformations. Write an equation for y is equal to the absolute value of x with the transformations or translations. I usually say shift or slide, but translations is another word for that. Left 7 units, up 2 units, and we want to reflect that over the x-axis. Well, this means that we're going to have a c value which is equal to -7 because we're pushing the graph to the left as opposed to the right. We have a shift up, so our d value is going to be equal to 2. And the reflection over the x-axis means that our leading coefficient, or a, needs to be negative. And we don't have a stretch, so we're going to call that -1. So here are the values that we need to basically sneak into our parent function. And our final answer is going to be y is equal to, we have that reflection over the x-axis, so negative, the absolute value. We don't have anything mentioned in here about reflections over the y-axis or horizontal stretch or compression, so just simply x minus a -7, and our vertical stretch, our vertical translation or slide or shift is up 2, so we have a +2 at the end of this function, and we have y is equal to the negative or the opposite of the absolute value of x plus 7 plus 2. And that is the end of my last example. I'm Mr. Tarrou. Bam! Go do your homework.